Okay, so before we start in with section 8.5, I do want to let everyone know that even though we're ahead on the Pearson, you guys should probably try to do your chapter 8 if you haven't already done so. Because obviously we're going to get to where you're going to do your chapter 8 exam. So you don't want to have all of your homework and your chapter 8 quiz and then your exam. Like, you don't want to try and do that all at the same time. You want to be able to spread it out a little bit. I can tell you that I've done chapter 8. I've done sections 8.1, 8.2, 8.3, and 8.4. They didn't take me that long, and I literally just used our notes to reference. So I feel like if you did the same thing, you should be more than fine. I did already mention before some of you popped in that even though the past 2 days we've been able to cover 2 different lessons, we probably will only be able to do one lesson today. 8.5 is a bit of a beast in terms of the amount, sheer volume of notes. It's just a lot of information. So we are going to start and working with sum and difference formulas. We have them for sine, cosine, and tangent. Obviously, if you have those three, then you can go through and do the reciprocal for the other formulas. So you want to go ahead and write this theorem down. Be careful for cosine. It is opposite signs. So you will, if you don't pay attention to that, it will mess you up when you do your homework. So cosine alpha plus beta, you need to use a minus in between. And then for the subtraction or the difference formula, you use a plus in between. It is opposite for cosine. And I believe if you guys look up a like trig or calc cheat sheet, these formulas are definitely all on there. It is nice to have everything kind of in one nice location. So if you wanted, you could make your own. I would just use like either a really big note card or, you know, a printer page front and back. But I would really only put it on there like things like your identities, your formulas, that kind of stuff. All right, so let's do a problem using the sum and difference formula. Now this problem does not, this examples 1 and 2, for whatever reason, chose to do the same formula. I don't really know why, they just did. So, all right, if we look at the cosine of 105, is the cosine of 105 something that we typically know right away off the top of our head? If I asked you for the exact value of the cosine of 105 without plugging it into a calculator and giving me a decimal, would you be able to do it?
No.
No. Okay, so what we can do is we can break it down into an alpha and a beta where we do know those options. So 105, how can we create or get to 105 with 2 other angles? What do you guys think? What angles do you want to use?
45 and 60.
Perfect. Okay, so we're going to use 45 and 60. And so that we can try and do this without giving away the solution this time, let's work on how we would do that. So cosine of 105 degrees. And you just told me we're going to use the sum. So we're going to do cosine of 45 degrees plus 60 degrees. Okay, let me give you a quick caveat here. When you go to do your homework later, you always want to go with the closest option. So when I say that, you might be able to find later a difference of, say, 15, if they want a cosine or a sine of 15 degrees. 30 and 45 will give you a difference of 15, but so will, say, 135 and 150. If you use the later ones, your sines will be messed up, and then Pearson yells at you, even though in all reality, you didn't pick terrible options, you just went too far down. Does that make sense to everyone? So you want to try and go with the smallest options first, unless they give you some parameters. If they give you some parameters, that makes it a little bit different. So someone walk me through the cosine of the sum formula. What do we do here? What's your next step? So if we think back to the formula, remember we have cosine alpha first. So in this case, alpha is always the first angle. And then it's a sum, so we're actually going to do a subtraction. But now, as opposed to 105 degrees, we can easily look up in our chart or our memories. You guys are all younger than me, so your memories are probably better than mine. You guys can all look up or recall the cosine of 45 and the cosine of 60, and the sine of 45 and the sine of 60. So now we have a little bit more to work with, right? So we have the root 2 over 2 times 1/2 minus root 2 over 2 times root 3 over 2. Now here's another hint I'm going to give you for the homework. And I only say this to you guys because I've already done it, and I just don't want you to have the same headaches that I've had. You kind of have a little internal check if you had the same denominators, okay? So in the future, when you go to do a homework problem, if you can easily eliminate or reduce, you should not do that, okay? Leave it the way it is until you get to the very end, and then you can reduce. Because if you reduce too early, you just end up getting frustrated, and then you have to work backwards. So leave it as unsimplified as possible, and then you can simplify in the end. So here you can see we can bring this together. We'll have the square root of 2 minus the square root of 6 all over 4. When Pearson shows you this, like an example, they'll go through and they'll pull out the 1/4. It doesn't matter. It accepts it either way. However you guys feel comfortable doing it is completely up to you. That was example 1. Any questions on that? I can save it for you if you want. Okay. Now that you have that equation, we are going to go through and go through problem number 2. So example 2. I'm actually going to give you the statement so we don't have to go back into the PowerPoint just yet. So they want you to find the cosine of 5 pi over 12. So I'm gonna give you guys a few minutes to kind of think about your radians. And I want you to kind of tell me, or not kind of tell me, I want you to tell me what your thoughts are on how you would approach this. Now keep in mind, I did give you a little hint that they chose to stick with the first formula. So they chose to stick with additions. It is not wrong if you would like to approach this from a different way. I think I did email out to you guys a bonus opportunity that if you wanted to do opposite or different approaches to some of your homeworks, just email me the handwritten work and let me know like which section and problem it is, so I can go in and see how Pearson wanted you to do it versus how you also chose to do it. Like I said, it happened to me many times when I was working through it. I would be like, oh, I don't need to look at that, and I would do the problem, and I would get down to the same identity, and then I would look at it and I would type it in, and Pearson yelled at me. Okay, so Pearson, definitely, if they want a certain approach, you cannot get around it. They want that approach. But for me, if you would like the bonus opportunity, you may certainly give me your work. So does anyone know what radians you would use if they want to do a sum?
We could do pi 4 plus pi 6.
Very good. And you can have those interchangeable. I think I used pi to the 6th first and then pi to the 4th, but it doesn't really matter as long as you are consistent throughout your problem. So we're going to have cosine of pi over 4 and cosine pi over 6 minus sine pi over 4 sine pi over 6. Okay. So it's not too hard to get to these points. But like I said, it does get pretty significantly challenging a little bit, I would say. Not anything you guys can't handle, because I've seen what you guys can handle at this point, and you're pretty great. But just kind of little things that could potentially trip you up. They like to, in the about halfway through the problems for this set, they like to throw at you where you have to use your triangle trig so you can get the missing side, and then that helps you get the missing angle and cosine or sine. So just kind of pay attention to what you're doing and you should be fine. Again, you guys can see here that we have the same denominator, which pretty much is your internal cue that you did it. More than likely you did it correctly. Definitely a big red flag if you did not get the same denominator. Something went wrong. Okay. All right, so we are good there. Yes. All right, let's go back into the PowerPoint. And I'm just gonna scroll through these because we got the same answers. Here you go, you wanna write down your identity. So the cosine of pi over 2 minus theta will prove at some point that it equals sine of theta, as well as the identity sine of pi over 2 minus theta equals cosine of theta. Okay. All right. So now that you guys should have significant time to write that down. I keep hitting. Okay. All right, so this is the second sum and difference formulas that you have to deal with. These are the sign functions. And notice that for this case, if you have a sum, you have a sum in the work. And if you have a difference, you have a difference in the work. Trust me, it can get very confusing if you don't pay attention to what you're doing. Okay? So if you're going through Pearson and you're going through your homework and you're like, okay, I'm doing this great, I'm doing this right, and then Pearson tells you you're wrong, the first thing you need to check for is if you matched up everything correctly. All right. At the end, we have a summary page, so it'll be nice to have everything written out together. When you're ready, let me know and I'll get us back over into the whiteboard. And I guess now that everybody's in here, I will reiterate my public service announcement while you guys are writing this down. I understand you guys had your exam to turn in. And if you haven't turned that in, you have, I think, until tomorrow night or tonight. Either way, you can turn it in either night if you haven't turned it in yet, because I'm still working on I haven't even touched the exam key yet. So no worries if you haven't turned it in yet. Additionally, though, if you haven't already started on chapter 8 for the Pearson, you want to go ahead and start on chapter 8 for Pearson. You don't want to let that back up. And I know we're a little bit ahead, but trust me, we have plenty of work to get through. And the fact that we somehow were able to get a little bit ahead with chapter 8, I will take it. I'm very, very happy that we have gone through chapter 8 so quickly using these PowerPoints. So, all right. So for this problem, we're going to look at sine of pi over 12. And that's obviously a radian we're not used to seeing. So we're going to have to choose an alpha and a beta. So what would you guys think our alpha and our beta should be? And because if you use a sum, the order doesn't really matter as long as you keep it consistent. So whatever's alpha is alpha, whatever's beta is beta. When you're using a difference, it matters, obviously, because it's not as cumulative, cumulative. Yeah, it can't be moved around much. You guys know what I'm saying. All right, so what radians will give us a difference of pi over 12? If you need help, let me know. But I'm more than willing to let you guys work it through. What do you guys think? You need to find a difference of pi over 12.
I got like 5 pi 6 minus 3 pi 4.
Okay, so that would be an example where we've kind of gone too far. Remember how I told you, like, because of the way the curves work, we could go potentially too far. So you're right, it probably does give us a difference of pi over 12, but what we're going to use is pi over 4 and pi over pi over 6. Okay, so you can see that we would have 3 pi over 12 minus 2 pi over 12, which would give us pi over 12. Your answer would probably fall in the realm of being correct, but possibly just with the wrong sign. So it might be positive where we're going to get a negative, or it might be negative where we're going to get a positive. So you just have to be careful of that when you're working through these. I would probably only take off maybe a half a point or a point on your exam, whereas Pearson will mark the whole thing wrong. So, all right. So now we're looking for sine pi over 4, cosine pi over 6, minus cosine pi over 4, sine pi over 6. Now, you guys can choose to do however you like. I chose to stick with how the textbook did it. I think their only rationale is that you want to have alpha, then beta, alpha, then beta. If you prefer to have sine and cosine and sine and cosine, that's fine. Just don't mix up your angles, okay? You have to keep those straight in your head. All right, so then we get radical 2 over 2 times radical 3 over 2 minus radical 2 over 2 times 1/2. Again, you guys can all see that we have the same denominators. This time we can pull it out just because why not? So 1/4 radical 6 minus radical 2. Now again, my guess would be if you went with the other angles, then you probably would have gotten either radical 6 plus radical 2. You could, like, somewhere there would just be a sign difference, because the answer, the main answer itself would probably be still very similar because of the way the curves work. All right. So for example 4. All right, I'm gonna go ahead and clear that. I already saved it in case you guys need to see it again later. So for example 4, we're kind of using the definition of what the sine values are. So we're gonna look at sine of 75 degrees, cosine 15 degrees. That's a 15, not a 3. Plus cosine 75 degrees, sine 15 degrees. So right now, with the way you guys are used to doing things, can we easily identify what the sine of 75, cosine of 15, cosine of 75, and sine of 15 are? Do we know that in any chart or off of our heads? No. But what we do know is, what is that representing? What does that formula remind you of?
the formula of sine of alpha plus beta.
Mm-hmm. Exactly. So we're going to go through and we're going to rewrite it. So sine of 75 degrees plus 15 degrees will give us the sine of what, really?
Of 90.
90. So what is the sine of 90 degrees? Anyone?
1.
Excellent. Okay. All right. So the next example that we're going to go over, this is an example you definitely want to take note of for the Pearson work. It is pretty intense. It kind of goes over everything we've learned, brings it all together, as math should. So if we are given if we are given sine alpha equals 1 over radical 2 or radical 2 over 2, if you rationalize correctly. But we have a restriction, pi over 2 less than alpha less than pi. And we are told that sine of beta equals negative 1/3. And we have the restriction that pi is less than beta, which is less than 3 pi over 2. Then they want us to find, then they say find the following exact values. Okay, and they want us to look for cosine of alpha, which I'll just draw that in. They want you to find cosine of beta. Then they want you to find cosine of alpha plus beta. And then lastly, sine of alpha plus beta. So let's fill those in. So cosine of alpha, cosine of beta, alpha plus beta, and then sine alpha plus beta. But if you guys take a look at what we're given, we are given sine of alpha and sine of beta. Does it seem like at this point that we have enough information to move forward? What do you know you're going to need to find? They kind of tell you, right? In parts A and B, we have to find the cosines of the given information. So before we can do anything, we have to figure out our triangle, right? Okay, so bear with me as I try to draw this as good as possible for you. want you to move. I want you to draw. Stop it. Oh, this is making me cranky. Ha! Bet you guys didn't know I could do that one. Look how nice that is. I don't think I could do it again in a million years. So, now that we have that, that's alpha. Okay. And then what other information do we know? This is the square root of 2. This is 1. So then this point is A1. Not to be confused with the steak sauce. There's your dad joke for the day. So now what do we do? Now that we have all that, what can we do? How does that help us?
We could use the given measurements to find the adjacent leg.
Yeah, we need to find A, okay? So to do that, which let's move this up a little bit so it's out of the way, but still kind of there. All right. So we have to find the distance. We know that the distance from A1 to 0, 0 is the square root of 2. So we know that A squared plus 1 squared equals radical 2 squared. So then A squared equals what? Well, radical 2 squared is just going to give us 2 minus 1. Okay, so A is equal to radical of 1, which is just equal to 1. Okay, and A is greater than 0. So we're going to take the positive. Right? Now that we know that, can we find the cosine of alpha? Yes. Cosine of alpha is equal to A over R, which means it's what? What do we know? We know it's going to be, oh, my apologies. What do we know about A? It should be a -1, right? So -1 over radical 2 will give us a negative radical 2 over 2. Okay, so that is the answer for A. Now we need to find cosine of beta. Okay, there is an alternative method to finding the cosine of alpha. You could also use one of your identities. I will show you that in the slide when we get back to it, just so you guys can have an easier time writing it down. Before we find cosine of beta, we have to do a pretty similar technique, right? All right. So I'm going to assume you guys know how to do that, and I'm not going to waste any extra time doing that. I am going to let you know what the beta works out to be. So again, it's going to be A over R. A ends up being negative radical 8, which would be -2 square roots of 2 Don't know why I wrote that down like that. Hold on, let me see. Why did I write that down like that? Ah, I just had a typo. That's all right. It's in my notes, not in your notes. We're all good. I just have to get back to where I was. Okay. All right, everything's good. So you end up with a negative 2 radical 2 over 3. Okay. Once you have those two items, what can you now do? What can we now find now that you have cosine of alpha and cosine of beta? You guys think you need some more space for it? Do you want me to do a clean sheet? Or do you want me to just squeeze it in? So if we do cosine of alpha plus beta, you will end up with 4 plus radical 2 all over 6. Okay. And then the last one, just so we can complete it out, for D, you have sine alpha plus beta, and it ends up being negative 4 plus radical 2 all over 6. And you guys can go through those. You can go through and prove that to yourselves. Okay. All right. Okay, let's get you back into the examples. All right, so you guys were interested. Is anyone interested in the alternative methods? I'll show them to you real quick. Okay, so here's the first one. Alternatively, you could have found cosine alpha by using the identity. Cosine alpha equals negative radical 1 minus sine squared alpha. You can see that would be negative square root of 1 minus 1/2. So you would still end up with negative radical 2 over 2. All right? So that's one option. You can do the same thing for cosine of beta. All right? So, okay, so let's look at example 6. The first step that you do there is you have to split the fraction. Once you split the fraction, you can see that you do end up having a +1, and then you can very easily find your cotangent in your cotangent alpha and your cotangent for beta. Any questions on example 6? Excuse me. Any questions up to this point on cosine and sine before we move on to tangent? Okay. As long as you work through the problems with the formulas, you should really be pretty fine. Okay. Go ahead and write out the sum and difference formula for the tangent function. What do you have to be careful of here? Anybody see what?
When you're in the denominator, the signs are opposite of each other.
Exactly. Okay. So if you're going to make a mistake on tangent, that's probably where you'll make your mistake. So honestly, just double check everything before you go ahead and do it. All right. The next two examples have us dealing with establishing the identities. Not really going to go through and explain them unless you need something explained. So please take a look at them, write them down, and let me know if you need anything explained on it. If you don't feel comfortable asking out loud, you can always use the chat. Okay, so here we're looking at the tangent of theta plus pi, and we need to prove that it's going to equal just the tangent of theta. Well, we know that tangent of theta plus tangent of pi is just 0, so that leaves us with tangent of theta on top. The tangent of theta cancels on the bottom because it's multiplied by 0, so we just end up with tangent of theta. All right. Well, the next one, they want you to prove that the tangent of theta minus pi over 2 will leave you with the negative cotangent of theta. So the first step they take is they choose to, instead of going through and working it as a difference for tangent, they choose to go through and work it for sine and cosine. Now, if you wanted to work it through as a tangent difference, I'm sure if you did that, you would still end up with the same answer. Okay? It's just a different approach. Any questions on this one? Okay. If you have questions, now would be the time to ask them. Okay. For the next one, we're actually going to make use of the inverse functions a little bit, but then they just turn around and rewrite them, so don't get too excited. It's pretty much the same thing you've been working with. So they give you that the inverse cosine of 1/2 plus the inverse sine of 3/5, and they want you to find the sine of that. Well, if we rewrite it so that alpha is equal to the inverse cosine of 1/2 and beta is equal to the sine inverse of 3/5, then we can find that cosine alpha equals 1/2 as long as we pay attention to the restriction. And then sine beta is equal to 3/5, again, paying attention to your restrictions. Okay? We're going to use the Pythagorean identities to obtain sine alpha and cosine beta. So we get radical 3/2 and 4/5. What's another method you could use? Well, I guess it's a similar method, but if you needed to, you could do what? What's something that I always recommend you guys do? You could have drawn the triangle, right? You could draw the diagram, right? If you plug everything in, you will get radical 3 over 2 times 4/5 plus 1/2 times 3/5, and you end up getting 4 radical 3 plus 3 over 10, right? Any questions on that example? Okay. You will have examples that are like this in the homework. So if you need to either come back to your notes or come back to the PowerPoint, it'll definitely help walk you through it. All right, the last portion that we're dealing with is writing a trig expression as an algebraic expression. Okay? So the first thing you have to do is you have to set sine of alpha equal to u and cosine of beta equal to v. You have to pay attention to not just your alpha and your beta limits, but also your u and your v limits. Okay? Go ahead and make sure you write all that down. Okay. Because negative pi over 2 is greater than or equal to alpha, and then alpha is less than or equal to pi over 2, that means we're looking at a cosine of alpha that's greater than or equal to 0. So we end up with the cosine of alpha equal to the square root of 1 minus sine squared alpha. So if we pay attention to your substitutions, you're going to get cosine alpha is equal to the square root of 1 minus u squared. Similarly, sine beta is going to be the square root of 1 minus v squared. So if we shove everything in, we end up getting uv plus the square root of 1 minus u squared times the square root of 1 minus v squared. Okay? That is definitely going to show up in Pearson. Might end up showing up on your exam. I'm not really sure. Haven't made it yet. All right. Example 11. We're looking at solving a trig equation linear in sine and cosine. Okay. So you have two different options with this problem. Both options are absurdly long. So whichever approach you take, you will have to deal with the same amount of work. Option 2 does have a diagram, whereas option 1 does not. So, I mean, I guess that's a difference to you. So for option 1, attempts to use available identities do not lead to equations that are easy to solve. So given the information, we have to square each side. So if we square each side, you're going to have to remember something later on, okay? So here you can kind of see how they work things. They squared each side. You get sine squared theta plus 2 sine theta cosine theta plus cosine squared theta equals 1. Then they went through and they solved. And now we're going to set sine theta and cosine theta equal to 0. So when we do that, it kind of looks like option 1 is a little bit nicer. What do you have to remember to do? We found 4 options. What do you have to remember to do? We squared the original, so what has to happen?
To like fit in the restriction.
Right, we have to actually plug them in to see if they're truly solutions or not. Okay, so when you plug them in, you actually find that pi and 3 pi over 2 do not fit the situation. So because of that, your solution set is only 0 and pi over 2. Okay, that is option 1. Option 2, we start with the equation, we divide both sides by the square root of 2. Okay, when we do that, if you take a look at your formulas, you're now looking at sine theta plus phi. Well, that's something we've been working with the whole time this lesson, right? We've been working with the sums of sines and cosines and tangents. So you end up finding that the sine of theta plus phi is equal to the square root of 2 over 2. So then that tells you that the cosine of phi is equal to the square root of 2 over 2. The sine of phi is equal to the square root of 2 over 2, as long as phi falls between 0 and does not yet approach 2 pi. So then the angle for phi has to be pi over 4, and then we end up getting sine of theta plus pi over 4 equals radical 2 over 2. But now you have to remember your interval, right? You're between 0 and not yet reaching 2 pi. So then you end up with the same solution set, 0 and pi over 2. Now, totally your option on which approach you take. Clearly you can see that approach 1 kind of deals with a little bit less trig and more algebra, but then you have to check for extraneous situations, right? You have to make sure that everything in your solution set actually does work. So in that sense, you're doing work twice. On the other hand, if you take the more trig approach, you're doing the same amount of work, but once you get to the answer, you're done. Again, totally your decision on how you want to approach it. I'm fine clearly with either option. All right, example 12. This is our last example, I'm pretty sure. Let me double check. Yes. Okay, so we're looking at the solving a sine theta plus b cosine theta equals c, where a, b, and c are constants in either a is not equal to 0 or b is not equal to 0. So we're going to divide each side by the square root of a squared plus b squared. You can take a look and see how that works out. Once you do that, we then start bringing phi back into play. So we eventually end up getting, let's bring this back in, equation right here that satisfies equation 11. Okay, obviously they have a nice little diagram there that helps you get to that point. Lastly, when we solve it out, okay, here we find if the absolute value of c is greater than the square root of a squared plus b squared, then that means that sine of theta plus phi has to be greater than 1, or the sine of theta plus phi has to be less than -1. Okay, so therefore there are no solutions in that situation. If the absolute value of c is less than or equal to the square root of a squared plus b squared, then the solutions of the equation are inverse sine of c square root of c over the square root of a squared plus b squared, or pi minus that solution. Okay, so in that situation, you're kind of looking at more of an abstract solution. All right, you can kind of use this example where if you find the situations that fit into this, then you can easily say, well, it has no solution, or you can plug things in and you can find those solutions. Okay, so this is probably a really hefty example for you guys to write down and work through later with other examples mixed in. It's a pretty good one. Here's your summary. All right, your sum and difference formulas, all nicely written there with a little bow on top. Okay. Does anyone have any questions for me?
No.
No. Okay. Before we go then, what I would like to address is